Alright, for example 1 of finding the flux, we just have the square with a 2 meter side, and the field is going through the square at a 60-degree angle to the normal. So if we define the magnitude of the field as 2 times 10 to the 4th newtons per coulomb, and we want to find the flux, we know that flux is the dot product between the field and the area. Dot product is going to simplify down to EA cosine theta, and we just do a simple plug-in. You've got 2 times 10 to the minus 4 newtons per coulomb. You've got the area of the square, and then cosine of the angle. Be sure your calculator's in degrees, and when you do the algebra, you end up with 4,000 Newton meter squared per coulomb. And here's a second example. If we want to know what the flux is through a circle of radius 3 meters in a uniform field. So we've got this random circle sitting kind of in a field. We have the electric field coming in at an angle. So we've got the vector definition of the field is 3J plus 5K times 10 to the 4th newtons per coulomb. And we're going to put the circle on the XY plane. So we've oriented it so it's just laying flat with the field kind of going through at an angle. So we set up the integral where the flux is equal to the integral of E dot NdA, and plug in our field, and our K hat is our normal to the circle, and we have dA still. So it ends up being the 5 times 10 to the 4th, because J dot K cancels out. You have 5 times 10 to the 4th newtons per coulomb times the integral of the area, which is pi times 3 meters squared, pi r squared. And we end up with 1.4 times 10 to the 6th Newton meter squared per coulomb squared.